Hi guys! Welcome to another Solve Reactions with Me video. Today we're gonna solve these 4 reactions from a real organic chemistry exam that I had back in the days. So in the first reaction we have alcohol on the left side, and on the right side, if you take a closer look on this new group hanging on the cyclohexane, you will see that here we have an ester. So basically now we need to convert an alcohol into an ester, and this can be very easily done just by mixing this alcohol with the corresponding carboxylic acid in acidic conditions. And by this I mean addition of some strong acid to our reaction mixture, like for example sulfuric acid. The reaction in this case is reversible, and it is basically just a formation of water molecule from the hydroxy group of the carboxylic acid and the hydrogen atom from the alcohol. So when the water molecule is formed, the remaining molecule parts bind together and form an ester. Now you can nicely see that the first residue is coming from the alcohol, and in our case it is the cyclohexane, and the second residue is coming from the carboxylic acid. It is a metal group in our case, and now if we add a carboxy group to the residue 2, we get the acetic acid, CH3COOH. Okay, I'm gonna write down our solution for this reaction first, and then we can take a look on the reaction mechanism. So in the first step, our carboxylic acid gets protonated by a strong acid that we add to the reaction mixture as a catalyst. A strong acid, like for example sulfuric acid, is a source of protons that exist in the H3O+ form in aqueous solutions. The protonation happens by a nucleophilic attack of the oxygen on the partially positively charged proton of the H3O+. As a result, we get a protonated form of the acid that can also exist in another form that is called a resonance structure. This is very important because in the resonance structure below, you see that both hydroxy groups are actually equivalent. So there is no difference between the upper and the lower oxygen atoms. Both structures can freely convert into each other anytime. Then our protonated carboxylic acid reacts with the alcohol. Since the oxygen has 2 lone electron pairs, it acts as a nucleophile and attacks a partially positively charged carbon, forcing the double bond to break. As you see, the oxygen atom from the alcohol now has 3 bonds and carries a positive charge. So in the next several steps, a sequence of proton rearrangements happens to eliminate this positive charge. In these steps, water acts as a carrier for this proton. Now the molecule is neutral, but you see that we have 3 oxygen atoms hanging around 1 carbon. It is a lot, considering also the fact that oxygen is more electronegative than the carbon. Each oxygen atom draws the electron density towards itself. So this molecule is actually incredibly unstable, even though it is already neutral. That is why another proton transfer happens, a water molecule is formed, so we can cleave it away. Water is generally a good leaving group. That is why a formation of water molecule is usually very favorable. As we remove the water molecule, of course a positive charge stays on the carbon. That is why at the same time the proton from the upper oxygen gets transferred onto the water molecule. And as a result, we get a neutral final product, an ester. And we also formed the H3O plus back, which totally makes sense because, as you remember, H3O plus was just a catalyst for the whole reaction. Okay, let's go to the next reaction. Here it might seem to be complicated at first sight, but what we can recognize in these structures is that the first molecule has a ketone group and the ester group. And in the product we have an alcohol group instead of ketone, but the ester group stayed intact. That means we have to deal with a partial reduction of the keto group to the alcohol group. And as you see, this reduction is very selective. The ester group was not reduced at all. So we cannot just use something like hydrogen gas for the reduction. Such a selective reduction can be achieved with the addition of sodium borohydride. In sodium borohydride, boron has 4 bonds with hydrogen atoms, and even though the common net charge is negative, boron itself is partially positive because it has actually a lower electronegativity than hydrogen. Basically, you can consider hydrogen here as H-. It acts as a nucleophile in this case, and so we have a classic nucleophilic addition to the keto group. Double bond breaks, hydrogen atom stays on the central carbon of the keto group, and the negative charge is transferred to the oxygen atom. This reaction happens in ethanol or any other common alcohol, and so in the next step, ethanol provides its proton to cover the negative charge. As a product, we get ethanolate, an ion, but also remember that we still have sodium in the system, so at the end we get sodium ethanolate as a byproduct. Time for the third reaction. What do we have here? On the left side we see a triple bond, so we are dealing with an alkyne, and as a product we have a ketone. As you probably know, the most typical reaction for alkynes is electrophilic addition, and since we have an oxygen in the product, we can assume that it was the addition of water. Hydration of alkynes requires catalysis, and usually it is either acidic catalysis or mercury catalysis. Now I will show you the mechanism of this reaction catalyzed by mercury, but of course it looks almost the same if you do it with the proton instead. So first, the positively charged mercury gets attracted to the very electron-dense triple bond. One of the pi bonds breaks and mercury binds to both carbons. Just consider this as kind of an activation step for the molecule, because now a water molecule can easily disrupt the second pi bond. Mercury is left only with one bond now, so it has a positive +1 charge. And the oxygen has 3 bonds in total, 2 with hydrogen atoms and 1 with the carbon, so it is also positively charged. Now, of course, this intermediate will try to achieve some neutral state, so what it can do, it can transfer one proton from the oxygen to another water molecule that we anyway have around as a solvent. And now our molecule carries only one positive charge. At this stage, the so-called keto-enol tautomerization happens. Hydrogen shifts from the oxygen to the carbon, and at the same time the double bond shifts to the oxygen. Now, what do we have in the system? We have a ketone and the H3O+ from the previous step. The keto group gets protonated by this H3O+, and this leads to two events. The double bond between oxygen and carbon breaks to accommodate the proton, and if it breaks, it means that the carbon would actually have only 3 bonds and would be positively charged. This would be a very unstable situation, at least because we would have electric repulsion between two closely positioned positive charges. To avoid this, mercury gets released so that the carbon atoms can form a new double bond. And now you see mercury was indeed just a catalyst for the whole reaction. We used it in the first reaction step and now we regenerated it back, so it was not used up in the reaction. And yeah, it makes sense. Now again, we have an alcohol group at the double bond, so the second keto-enol tautomerization event happens. As you remember from previous steps, keto-enol tautomerization is basically just a simultaneous shift of the proton from hydroxy group and the double bond between carbons. And here is our final reaction product, the acetone molecule. And this is our last reaction. On the left side, we have an alcohol. And on the right side, we have an amine. So we need a reaction to convert an alcohol into amine, and this can be easily done with the simple addition of ammonia with a catalyst. For example, you can take nickel. This reaction follows the so-called hydrogen borrowing mechanism, meaning that the catalytic metal, in our case it's nickel, it can absorb hydrogen on its surface. So basically it takes both hydrogen atoms around the most polarized group, and the alcohol molecule gets converted into a ketone. Now, when we add ammonia to a ketone, we have a classic nucleophilic addition. Nitrogen, as a nucleophile, attacks a partially positively charged carbon. A new bond is formed between this nitrogen and carbon, and of course now nitrogen has a positive charge because it has 4 bonds in total. On the other side, oxygen has only 1 bond, so it is negatively charged. Then a proton transfer happens and the molecule gets into a neutral state. And now remember, we had nickel with absorbed hydrogen atoms after the first reaction step, and since the metal acts only as a catalyst, meaning it doesn't get used up in the reaction, it gives the hydrogen atoms back so that a good leaving group, a water molecule, can be formed, metal is regenerated back, and finally we have an amine as a product. Okay guys, that's it for today. I hope this video was helpful for you. Let me know in the comments below if you have any questions or if you have any reactions on your mind that you want to solve with me next time. See you in the next video. Bye!